Everybody, welcome to our new chapter. We are in chapter 3, section 1. We're going to look at derivatives of polynomial and exponential functions today. If you remember, when we were talking about derivatives in the last chapter, we sort of left off by describing them as these instantaneous rates of change. We talked about it in terms of like velocity, but one of the words we used to describe a derivative was that of slope. And so what we're going to do is we're going to sort of expand on that idea and see how by recognizing that a derivative represents slope, how that can help us to determine the derivative of certain types of functions. So for example, one type of function that you will be differentiating is that of a constant function. So let's take the constant function. And this will be a function of the form f of x is equal to some constant c. So one way we could think about this, like as a particular case, would be an example where we have the function f of x is equal to 3. Okay, so think about what that means. F of x equals 3, or maybe if you prefer to think about it this way as y equals 3. This is a horizontal line through the point when y is 3. So if we were to make a quick sketch of this, throw an x-y axis on here. And the graph of this, we'll use a different color, would look like this. Here is f of x equals 3. Now, the question that I would have is, what is the derivative for this particular function? Well, keeping in mind that derivative means the same thing as the slope, that's the equivalent of me saying, what is the slope of this function? Well, if you recognize that because it's a constant function, that it's going to give you a horizontal line when you graph it, and given what you already know about horizontal lines, which is that they have a slope of 0, then the answer to my question of what is the derivative, you would say, oh, well, the derivative is just 0. So we could state that the derivative, and maybe I'll just say slope, just as a reminder, the derivative or slope of a constant function is 0. And that's going to be for any constant function. It doesn't have to just be at 3, right? I mean, if you move this function up or down, it's still going to be a horizontal line. The slope everywhere is going to be 0, therefore the derivative is 0. So the way we're going to think about this just in terms of, like, say, a formula or definition would be to say the derivative. So remember the notation we went over in the last chapter. D over dx is a command saying take the derivative of this thing with respect to x. I'm just assuming our function is an f of x function. So the derivative with respect to x of some constant, let's call it c, this is going to be equal to 0. So we'll go ahead and color this a little bit so that we don't forget this idea. So the derivative of a constant is 0. In fact, you should just say that to yourself a few times over. The derivative, actually, I don't know why I'm about to write it again. I just wrote it. The derivative of a constant is 0. The derivative of a constant is 0. It's going to be one of those things where, you know, if we're allowed to be back on campus again, you know, assuming no more pandemic, and I see you on campus and I'm like, hey, how was the class? And you're like, oh, it was great. I remember all kinds. And I'm like, okay, well, what do you remember? At the very least, you should be able to tell me, oh, the derivative of a constant is 0. You tell me that, I'll be happy. I'll leave you alone. I won't quiz you anymore. Okay, so derivative of a constant is 0. Easiest derivative you need to know. Okay, what if the function changes though? Like, let's pretend it's not f of x equals c. What if we have a different type of function? So what if the function is f of x is equal to x? And my question for you is, okay, well, what is the derivative of this function? So you could again sort of think about it in terms of the graph of what would happen if you dealt with the graph of f of x equals x, and you should all know what that is off the top of your head, right? It's going to make a line. It's going to have an intercept the origin. And it's going to look something like this. Maybe like that. All right, maybe that's off by just a little bit, but you get the general idea, right? This is f of x equals x. So if I said, well, what is the derivative of this function? Well, that's the same thing as me saying, what is the slope of this function? So the slope of this function, we'll just look at it. F of x equals x. Remember back to your very early algebra days when you learned about equations of lines, and you learned them in this form, and you learned that the number in front of x, that's the slope of the line. So in this case, the number in front of x, the coefficient of x, is 1. So we would say the derivative, or again, the slope if you prefer, right? The derivative of f of x equals x is 1. Now the way we would write that is using our proper notation. So the derivative of x, well, that's just equal to 1, okay? Now notice that's the derivative of x with respect to x. We will deal with later on mixing those variables up so that they don't match, but for right now, just assume the variables are always gonna match. Okay, so the derivative of x with respect to x is just 1. And we'll go ahead and save that one as one to remember. And then, you know, speaking of the y equals mx plus b that I just mentioned before, what about for any line? What's going to be the derivative? So what about any line? Like, what's the derivative going to be there? Well, if it's just any line, then any line would take on the form f of x equals mx plus b. And if I say, well, what's the derivative of this? You would just say, well, the derivative is the slope, and the slope of this general form of the line is m. So we could write that the derivative with respect to x of mx plus b, well, that's just equal to m. It's equal to the slope of your line. All right, well, this seems like a pretty convenient thing to know, because what this is allowing us to do is to find slopes without having to use that limit definition. But the problem is this sort of shortcut, if you will, is only working because all of the functions we're talking about are straight lines. So what about the functions that are non-linear? How do we deal with those? So this is going to be perhaps the most powerful thing I can show you in this class. This is going to be one of those techniques that is going to save you so much time and make taking derivatives so very easy. So how do we deal with derivatives of non-linear polynomials? All right, so derivatives of nonlinear polynomials. So perhaps the most famous nonlinear polynomial that you've had to deal with over the years has been this one of f of x is equal to x squared. So this does not make a straight line. The coefficient of x squared does not represent slope. So if I said, what is the derivative of this polynomial? Well, up until now, the way we've been able to resolve that is by dealing with the definition. So if you remember the definition that we would go through, right? It was the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, what I'm going to do is I'm going to show you, and I'll do the limit definition just so you can, just to kind of prove it to you here. But my claim is this, without working this out, my claim is that when we go to take the derivative, so we can express that as f prime, right? That's one way to talk about the derivative. F prime of x is going to be 2x in this particular problem. Now, the way I know that is because I know a special rule that allows me to do this, but let's just verify it with the definition here just to make sure that I'm not just making things up. So the limit as h goes to 0, f of x plus h. So that means plug x plus h into the function, so x plus h squared, and then subtract the function, so subtract x squared. This is all over h. Now what we want to do, remember, we got to get rid of that h in the denominator. So let's expand everything out in the numerator, and we'll get the limit as h goes to 0. The numerator is going to be x squared plus 2xh plus h squared minus x squared. And that's all over h. And then we'll notice that the x squareds cancel. And that's what we expect. If you remember back to the end of the last chapter, we want all the non-h containing terms to go away. All the terms that are left over in your numerator, this one and this one, those both contain an h. And that's what we want because remember, we want to factor out that h. So this would be the limit as h goes to 0. If I factor out an h from the numerator, I'm going to get 2x plus h over h. And now that problematic h that we had in the denominator is gone. We cancel that out. And so from here, we get the limit as h goes to 0 of 2x plus h, where this h, when you plug in 0, just goes away. And so all that we're left with is 2x. But notice that that is exactly what we got at the beginning. Okay, so the question then is, how do we go from the function x squared to getting the derivative of 2x without having to use this limit definition that we worked through here in green? Because that was, a handful of steps, and sometimes the function can get a little bit obnoxious and maybe the algebra gets very intense. So what is this trick to doing this? Well, let me show you. So let me show you by just looking at another example. So instead of x squared, what if I would have said x cubed? We worked out something like this before in terms of finding the derivative by using the limit definition. And it's a little bit more work, right? Because it's to the third power. So when you have to expand everything out in that second or third step, you have to know how to multiply that out to the third. So if you know about binomial expansions, maybe it's not as bad. But if you don't know about them, it's a real pain because you're basically foiling and then foiling again. And it becomes very cumbersome with all this multiplication and combining like terms and all this stuff. So what if I just told you that the derivative of this was just 3x squared? No work required other than just knowing this trick. Now, some of you already know the trick, right? So this is not news to you. You're already well aware of what's going on here. But for those of you that don't know what's going on yet, can you look at what we did with x squared and now what we've done with x cubed, and can you figure out what's happening? Let me try another one. What if it was x to the 4th power? Now, this could be solved by using the limit definition, but this one's going to be even a bigger pain than x cubed, because again, it all boils down to every single time, no matter x to the whatever, you have to expand it out to be able to cancel terms, to be able to take out that h so that you can cancel the h with the h in your denominator so that you can actually figure out what this limit's going to be. So the derivative here for x to the 4th power, that's going to be 4x cubed. Do you see the pattern yet? All right, so we had f of x equals x squared, and I told you that the derivative was going to be 2x. And then for x cubed, we get 3x squared. For x to the 4th, we get 4x cubed. You start to see the pattern. Maybe if I throw this here. Remember, the exponent when you don't see it is really 1. All right, well, if you still don't see it, I'm just going to tell you now. The way you're going to deal with any kind of power function, let's say f of x equals x to the, let's just call it the nth power. All right, we'll just pick some random value for n here. So if f of x equals x to the n power, then what you're going to do, if you want to find its derivative, is to take f prime of x is equal to, So whatever your power is, whatever that number n is, that gets moved to the front and becomes a coefficient that's being multiplied. So it's going to be n times your base is x, and then the exponent where the n was, if you'll notice in the ones we've done, that reduces by 1. So this is going to be n minus 1. So this important derivative is what we call the power rule. So this, we'll just label it off to the side. This is the power rule. And this is one that you will just use all the time. You'll use it all the time. I'm not even going to worry about you like suggesting, hey, maybe think about memorizing this rule because it happens so much. You will use this so much that you will not be able to help but memorize this derivative. Okay, so for example, now that you sort of, you know the trick, if I said, you know, what's the derivative of x to the, where'd we leave off? Well, let's just skip a couple. What if I said x to the 7th power? What would be the derivative? Well, the derivative of this, actually, I don't even need the arrow. It's just a straight equal sign will be fine. Bring the power down. Your base stays x. Reduce the power by 1. You get 7x to the 6th power. All right, maybe you're not that impressed with this, but what if I had asked you in the last chapter to compute the derivative of x to say like the 100th power? And I said, what is this? Think about what you would have had to go through algebraically to figure this thing out. You would have had x plus h raised to the 100th power, and you would have had to expand that out, right, by the definition. I don't think anybody wants to mess with that. So this is where the shortcut is really helpful. Power down front, base reduces by 1, you get 100x to the 99th, and it's just that simple. Okay, so I hope you are on board with that idea. Now, one thing that goes very, very nicely with this power rule is the thing called the constant multiple rule. So I want to talk to you about the constant multiple rule because we can't really do much with the power rule if we don't know the constant multiple rule. And the constant multiple rule is for dealing with a function that has a constant already in front of it. So for example, if I would have taken f of x, instead of just saying f of x is x to the n power, what if I said it was some constant times x to the n power? Then what would happen when you go to take the derivative? So the derivative of this, f prime of x, here's all that happens. That constant that's there, that just kind of gets to hang out. And what you're going to do when you bring that power of n down to the front of this, you're just going to multiply the constant with the value of n. So you're going to get c times n in front of the problem, and then your base is x, and then it's still to the n minus 1. So you're just going to multiply those two pieces together, and that's literally all it is. You just multiply the pieces together. But since most of the functions we deal with are going to have some constant out front, we need to know how to handle that. So an example of this might be something like this. Let's suppose f of x is equal to, let's take the number 30, and let's say we have x to the 3rd power. And I want to find the derivative of this. So what the constant multiple rule tells me is that when I bring the 3 down front, just multiply it with the 30. So 30 times 3, I'll write it out for you here this time, but most times you'll just do the multiplication in your head, or if the numbers are large enough, you know, if you need to use your calculator, but it's unlikely that'll be the case. So you're going to get 30 times 3 times x to the, and then your new power would be 1 less, so x to the 2nd. And then 30 times 3, of course, is 90, x squared, and there's your derivative. So the derivative of 30x cubed is 90x squared. And then you could keep going with this, right? You could take the derivative again, as we saw in the last section. You can do higher order derivatives. So we could differentiate 90x squared. In fact, might as well, right? Why not? Let's find the second derivative of this function. The second derivative is going to be the derivative of 90x squared. So in this case, the 90 is our constant out front. And now the 2 is going to come down front to join it. So we're going to have 90 times 2 times x. And now when your exponent was 2 and you go to reduce it by 1, now it's just minus 1. It's just x to the first. Don't need to worry about writing the exponent. We all know that what we see here just means x to the first power. So what this tells me, 90 times 2 is 180x. All right, so there's my second derivative. Now, could I keep going with this if I wanted to? Would this still, can I keep differentiating? If I wanted the third derivative, or f triple prime of x, I would take the derivative of 180x. Well, 180x, if you remember back to the beginning, 180x, that's just a linear function, right? This is like the same thing as looking at y equals 180x and me saying, what's the slope of that line? Well, the slope of that line is 180. So the third derivative is just the slope of the line, which is 180. Now, could we even go further? Yeah, we could. It's getting obnoxious now. I wasn't even planning on doing the second one, but we've gone down the rabbit hole. We have to keep going now. The derivative of 180. Well, 180 is a constant. First thing I told you in this section, as far as these rules were concerned, was the derivative of a constant. And the derivative of a constant is 0. So if we start with 30x cubed and differentiate, we end up at 90x squared. Differentiate again, we get 180x. Differentiate again, we get at 180. Differentiate again, we're at 0. Now we could keep going, right? We could take derivatives for the remainder of this lesson of just this one, but it's going to be quite boring because they're all going to just stay 0 at this point. And that's the thing that you're going to find when you're dealing with these polynomial functions like these here that we've been doing. Eventually, you're going to get to 0, right? It just depends on how big the power is that you started with, but eventually you'll get to 0. Okay, so the other rule that, or rules that I need to go over, so we've done the power rule, we've done the constant multiple rule. I want to go over what's called the sum and difference rules with you. And once we have these ones down, then we're going to be in a position to work out some examples, like some pretty nice examples, right? Not these real kind of maybe more basic ones that we've been doing so far. But the sum and difference rules are just this. So we're going to, let me just set it up for us. Let f of x and g of x be differentiable functions. So remember that word differentiable just means you can take the derivative. So f of x and g of x are differentiable functions. Okay, so what if I wanted to find the derivative of f of x plus g of x? So I have two functions here and I'm adding the functions. Now, assuming that the functions, you can't combine like terms and just write it as one single function. It is two distinct parts. Well, this is the same as taking the derivative of f of x and adding that with the derivative of g of x. So you can kind of think of this derivative command almost like you would the distributive property. And then the way you could write this would just be f prime of x plus g prime of x. Okay, so there's the sum rule. And then difference is the exact same thing, just instead of plus, you do minus. So if I said, what's the derivative of f of x minus g of x? This is going to be the derivative of f of x, and then minus the derivative of g of x. And this is just f prime minus g prime. Okay, so these two are probably very obvious, right? Because we had very similar rules when we dealt with limits. And so you're gonna see this often. with other things that we do in calculus as well. So when you're adding the pieces together, you're trying to take this thing being the derivative, take the derivative of these pieces, then that's just the equivalent of taking the derivative of each individual piece as you go. Okay, so now that we have the rules in place, what I want to do is I want to work through some examples with you. All right, so I've got a handful of them here, and they're all different types of functions that you're going to encounter. So I don't mean to browbeat you by doing so many examples, but I think this is going to be really helpful because you never know when you're going to encounter a certain type that you're just like, wait, how do I deal with one like this? So in this example, we want to find the derivative. And we're going to use all of these great shortcuts that we found, right? If we can find a way to deal with the constant, derivative of a constant, we will. If it's just a linear function, that'd be great. But if not, power rule, constant multiple rule, sum rule, difference rule, they're all going to show up here. So the first one we're going to look at, we'll just call it part A, is the function y is equal to 2/3 times x to the 4th power plus 5x minus x to the -1 power. And so what I want to do is I want to go ahead and figure out what in the world, oh, excuse me, not -1, sorry, that would actually be really bad if it was -1. It's -3. Sorry, you guys. Why would it be bad if it was -1? We're going to have to hold on to that if you're wondering, like, wait, why can't we do -1? We'll do -1 later. All right, that's a special case that we'll get to. -3 is what I meant. Okay, so what we want to do is we want to find the derivative of this function. So the derivative, one way we could notate that is by putting y prime, and your notation is going to be very crucial so that it's very obvious to anybody looking at what you're doing. You know, you want to let them know that you understand the difference between a y equals being just the function and y prime being its derivative. So we're going to start working out the derivative here. Okay, so first piece, 2/3 x to the 4th. So I see a constant being multiplied to this of 2/3, and I see a power of 4. So what I'm going to have to do is I'm going to have my 2/3 out front, and then I'm going to multiply that by the 4 that's moving down from the power rule. And then I have x to the 3rd power, replace it by 1 less. And we'll clean all this stuff up at the next step. And then plus, okay, well, what about the middle piece? It's just 5x. What's the derivative of 5x? Well, 5x is just, it's linear, right? It's like y equals 5x. The slope, or the derivative, is just 5. Now, if you're kind of struggling with the idea of, I'm worried I'm not going to recognize these linear pieces when they're sort of buried in between these nonlinear pieces, you can think about it this way in terms of the power rule. If you have y equals 5x, remember it's 5x to the 1st power. So if you go to take the derivative here, y prime would be 5, bring the 1 down front, you have x. Replace your power by 1 less. 1 take away 1 would give you 0. So y prime, you have 5 times 1 times x to the 0 is just 5, right? Because remember, anything to the 0 power is just 1. So that's another way you can think about how to get this one. All right, and then for the last piece, back to the problem we're on, your power is -3. You're going to bring that down to the front. Now, what's down front is a -1 is your coefficient. So it's going to be minus, and then you're going to have -3 that's being brought down to the front. Your base is x, and then when you reduce the power by 1, you're going to get -4. So we get y prime equals, let's just clean all this up, 2/3 times 4 is 8/3. So 8/3 x cubed plus 5, and then minus the negative is going to give us a plus 3x to the -4th. And you can leave it right there, or if on that last term you want to write it as 3 over x to the 4th power because you want to get rid of the negative, that's fine too. Okay, so there's one. Next one. Y equals -1/2 x to the 4th power plus 3 times x to the 5/3 power. So that's new. We have a fractional exponent. And then plus 2x. And we want to take the derivative. So let me use a different notation. I'm going to write dy dx this time just to mix things up a little bit. If you really hate that and you want to put y prime, go for it. All right, so the derivative of the first one. Well, we have -1/2 is the constant out front. That's going to get multiplied by the 4. Now, eventually, you're just going to do these multiplications in your head. You don't need to write out the product in front. I'm just doing that for these first few until you maybe get the hang of it. X to the, replace it by 1, so 3, plus, all right, we have a 3 down front. The power is 5/3, so 5/3 is moving down to the front. And then this is times x to the, all right, so 5/3 take away 1 is going to be 2/3. And finally, the derivative of 2x is just going to be 2. For the same reason, the derivative of 5x was just 5. And now all that's left to do is to clean up our answer. So -1/2 times 4, that's going to give us -2 x to the 3rd power, plus 3 times 5/3 is 5. So 5x to the 2/3 power plus 2. Okay, 2 down. All right, part C of our example. Part C of our example is going to really change things up, not only in terms of what we're looking at, but also in terms of the letters you're going to see. It's not always going to be f of x and y, right? Any letter combination can be used for writing a function, and so you have to be able to express the derivative in whatever, I swear I can talk, whatever variables are given. So let's suppose you have a function, let's call it f of s in this case, and it's equal to -3 over s squared minus 4 over s to the 4th. Okay, so we want to find the derivative. So let's, for the derivative notation, let's call it f prime of s. But as soon as I write f prime of s, I think, okay, I'm ready to take the derivative. Now I'm looking at these pieces and I'm thinking, wait a minute, how do I deal with it when I have my variable in the denominator? And the answer is you can't right now, right? There is a way to do these where they stay written this way, but we're not going to learn that until I think the next section. So for right now, what you're going to want to do, and even when you learn the next section, you're probably still going to want to do this because I think this is overall is going to be a little bit easier, is you want to rewrite the variable so that it can be up in the numerator. So you have -3, and instead of dividing it by s squared, I'm going to multiply it by s to the -2. Remember, if you change the sign on your exponent, you can move things from numerators to denominators and vice versa. And then this is going to be -4 times s to the -4. Okay, so we are now going to take the derivative this way because now the power rule, I think, is a little bit more obvious. So you have the -3 out front, and you're going to bring the -2 to join the -3. And then this is s raised to the, if we subtract the -2 by 1, we're going to get s to the -3rd power. And then we have -4 already out front. We're bringing down a -4. And then this will be s to the -5. Subtract 1 in your power. And then just simplify your solution. So f prime of s, this is going to be 6s to the -3 plus 16s to the -5. Okay, so hopefully that one makes sense for you. All right, let's look at another. This time, let's call it f of x again. We'll give you a break on the weird variables. And f of x this time is equal to 2/3 x to the 3/2 power minus 3/4 x to the 3/5 power. And we want to take the derivative. So, all right, notationally, I'll call it f prime of x. Everything seems to be written in a way that will work for us. I've got the 2/3 out front already. I'm bringing the power of 3/2 down. My base is x. When I replace, when I replace the 3/2 by subtracting 1 from it, 3/2 take away 1 is 1/2. And then on this second piece over here, we've got the 3/4 already in front. Multiply that by 3/5 x. And then when you subtract 1 from this, so 3/5 take away 1 is going to leave you with a negative 2/5 as your new power. And now let's just multiply out these coefficients. On the first one here, the 2/3 and the 3/2, those just become 1. So you get just x to the 1/2 power. On this other one, you're going to get not canceled. What is this? 9/20. Right? That's right. 3 times 3, 9, 4 times 5 is 20, times x to the negative 2/5 power. Okay, so fractional coefficients with fractional exponents, that's always a fun combination. All right, I want to do one more, and then I have one sort of final formula, I guess we can call it, to show you. So on this one, let's make it fun variables again. We'll go h of s. And this is going to actually, no, I take that back. I don't want to use s. My s's I feel like look too much like 5. Let's do h of t. So h of t is going to be equal to the square root of 2 times the cube root of t plus the square root of 2 times the 5th root of t. Okay. So what do we do when we want to differentiate and we have things in radical form? Well, the thing you do is you rewrite it. So I'm not going to take the derivative in this form. What I am going to do is I'm going to deal with rewriting those pieces. But the other thing that I want to notice here, which is interesting, is that both of these pieces are being multiplied by a root 2. So another thing that you can do if you recognize something like that happening is you can factor out a common constant, and then you don't have to sort of multiply that, kind of carry that through all the way. You can just sort of leave it alone and save it for the end. So if I factor out that square root of 2, that leaves me with the cube root of t plus the 5th root of t. All right, so that's one thing that's going to make lives a little bit easier. And then the other thing we're going to do is we're going to rewrite this. So the cube root of t, remember that's t to the 1/3 power. And the 5th root of t is t to the 1/5 power. All right, so now I'm ready to take my derivative. So h prime of t is going to be equal to, I'm going to go ahead and just leave that constant outside for right now. Okay, I don't need to carry it through when I take my derivative. So the constant can sort of get peeled off. Now t to the 1/3 power, bring the power down front, so 1/3 times t, and then 1/3 take away 1, it gives me negative 2/3. And then plus t to the 1/5 power, bring the 1/5 down front. Base is t, replace it by 1, you're going to get a negative 4/5 as your new power. And honestly, you can leave your answer like this. You don't need to distribute the root 2. You can leave the negative exponents, that's fine, unless you're specifically told to get rid of them, but I can't imagine that being an issue. There's your derivative. Okay, let's see. Just looking over my notes and I'm trying to remember if this is, yeah, let's go ahead and do this. Okay, sorry. I know I said I had one other idea to show you to kind of wrap it up, but before I get to that thing, I would feel bad if I didn't do this example with you as well. So it's going to require us to use all these rules we've been learning, but just in a different way. So what you're going to be asked to do in this problem is to find equations of the tangent line. So we've talked about those before, right? So that's the line that comes into contact with your curve in only one point. Find equations of the tangent line and normal line. Now that's a new one, and I'll explain what that is in just a moment. To the curve, and the curve that we're going to have is y equals x times the square root of x at the point 1, 1. Okay, so at the point 1, 1. All right, so first of all, you know what a tangent line is, right? A tangent line is a line that intersects a curve in one point. A normal line is going to be perpendicular to your tangent line. So just as maybe a note here, a normal line is the line perpendicular, where you can use the little upside down T symbol for perpendicular. A normal line is the line perpendicular to the tangent line. And the only thing you really need to know is this is not going to be that much added work. It's more just remembering something. If you have slopes that are perpendicular, remember that they are opposite reciprocals of each other. So lines that are perpendicular have slopes that are opposite reciprocals. Okay. All right, so now that we have that information, let's talk first about the tangent line. So how are we going to deal with finding the equation of a tangent line? What are we going to need? Well, first thing you're going to want to know is you're going to want to know what form are we going to put this in. So the form that we're going to use for this is y minus y1 equals m times x minus x1. If you remember, that's the point slope form of a line. That's the one that I'm going to always use when I do these. So if it's the point slope form, guess what I need? I need the point and I need a slope. So our needs list is going to be one, we're going to need a point, right? So some XY combination. And then the other thing we're going to need is the slope, but importantly, the slope at the given point. All right, so we're going to need all of these things to be able to find the equation of a tangent line. All right, so for the problem that we're dealing with, we were given a function y equals x root x. And I want to know what is the equation of the tangent line to this curve at the point 1, 1. Oh, hey, that's something, the point. The point is 1, 1. All right, so that was given to us. Well, that's convenient. So then how do I figure out the slope? Because this isn't a straight line, right? X times the square root of x, not a straight line. So shoot, does that mean it's no solution? It doesn't have one, what? Well, this is where you remember slope and derivative mean the same thing. So really to find the slope for this particular function, we need to find its derivative. So now I'm looking at the function y equals x times the square root of x, and now I'm thinking again, okay, even though I know I need the derivative, now I'm not feeling super confident about how do I take the derivative of that thing. Because again, I see x times the square root of x, and of all the rules we went over tonight, none of them discussed a function times a function. That's not coming until later in the chapter. So what I need to do is I need to find a way to rewrite this thing so that I can put it in the form of a function that I know how to differentiate. So what I might do is look at it and say, okay, well, x times the square root of x, well, that's just the same thing as saying x times x to the 1/2 power. And remembering something from your algebra days, which is when you're multiplying two pieces with a common base, you add your exponents. So this is going to be y equals, so if your exponent here is 1, you're going to get x to the 3/2 power. And that's a very common thing to have happen, right? I mean, why is it being written as x to the square root of x? So that way you'll know that you need to convert it, right? You need to change it into x to the 3/2. You're not going to take the derivative of it written like y equals x to the x times the square root of x. That's just stupid. Okay, that would be a pain in the butt. This derivative here is going to be a lot easier. Okay, so now that we have the function written in some form that we can kind of deal with, let's go ahead and take the derivative. Let's see what we'll use here for the derivative. So y prime, so remember how this works, bring the power down front, 3/2. X to the, now replace the power by 1 less, so 3/2 take away 1 is 1/2. Or if you prefer, you can think of it this way, as 3/2 times the square root of x, if you like that better. Okay, so here is a very, very common mistake that happens when somebody is trying to solve for the equation of a tangent line. So common mistake, and please do not let this happen to you. So a common mistake is to do this. So you know the point is 1, 1, right? So that's kind of like your x1, y1 value in the formula. So people would be like, okay, here's my equation. Y minus, what's the y value is 1, equals my slope. What's my slope? Oh, my slope is 3/2 root x times x minus 1, and they put a box around it, and they feel very good about themselves. This is not good. Specifically right here, this would be a no. When you're writing the equation of a tangent line at a specific point, you need to write your slope as a numerical value, right? You're not finding this right here is the slope in general, right? This is the formula for the slope at any spot along this curve. But what we need specifically is what is the slope at the point 1, 1. So how do I figure that out? I just plug 1 into the formula for my slope. So what I need to do here is figure out what is y prime of 1. Well, that's 3/2 times the square root of 1, which is just 3/2. So this is the slope of my line, right? So let's write that down. This is the slope of the tangent line. And this is the slope specifically of the tangent line at the point 1, 1. And that's what we want, right? That's the slope we want. So if you find yourself plugging in a function for the slope, stop yourself, right? You don't want to do that. You want to plug in a numerical value. So the conclusion that we're going to have to this problem is this. We're going to have y minus 1 equals, okay, the slope we want is 3/2 times x minus 1. And even though you don't want to, you're going to leave your answer just like this. A lot of you will try to write this in mx plus b form. There's no point to it. Right? You don't need to. It's not going to do us any good right now. Unless, you know, we're asked to then graph this line, then leave it alone. Don't do anything with it. Okay, now, the other thing that we were asked to do, right? So when I say conclusion and I write this, this is the equation of the tangent line. Now the other thing, oops, is that going to catch up, or is it, did we finally, nope, I think it finally had enough and said, I am going to be difficult now. So let's try to connect again. There it goes. There we go. Okay, so that's the equation of the tangent line. But remember at the beginning of the problem, it said find the equations of the tangent line and then also find the equation of the normal line. All right, so if I want to deal with the normal line, so we can do that down here. So for the normal line, remember, is perpendicular to your tangent line. So if your tangent line has a slope of 3/2, the normal line is going to have a slope that is the opposite reciprocal. So the slope of the tangent line was positive, so our slope for the normal line will be negative, and the reciprocal of 3/2 is 2/3. So there's your slope. Your point doesn't change. It's still 1, 1. So the equation of our normal line is going to look like this. It's going to be y minus 1 equals negative 2/3 times x minus 1. And if you look at it, it looks just like your tangent line, just with the change to the slope. Okay, so that is how we deal with that. In fact, let's just backtrack. Let's just do a real quick recap because that was kind of a lot of information there. All right, so just to remind you of what we did, we were asked to find the equations of the tangent line and the normal line for a specific curve at a specific point. So to find the equation of a tangent line, I told you that we're going to use the point slope form of a line, y minus y1 equals m times x minus x1. And then I said, these are the things you need. Anytime you're going to find the equation of a tangent line, you need a point. Now the point was given to us in the problem statement. It was at 1, 1. And then we need the slope at that point. So to find the slope, we had to take the derivative of the function they gave us. Now the function given had to be manipulated a little bit so we could use the power rule on it. We took the derivative and then we plugged in the point, right? Or at least the x value of the point, because that's all that we could really plug in there. We plug in the x value of the point and we got our slope of 3/2. And so we plugged in our point and our slope into the formula for the equation of a line, and we got our tangent line. And then to find the normal line, the only difference there is just in the slope, which is the opposite reciprocal of your tangent slope. So from 3/2 went to negative 2/3, the rest of it stayed the same. And there is everything. Okay, that is our entire process. All right, the last thing that I'm gonna leave you with is this here. So it's the derivative of the natural exponential function. So the derivative of the natural exponential function. It sounds like something that's going to be really terrible, but it's actually not. The natural exponential function is e to the x. And we want to know, how do we take, so how to take the derivative of f of x is equal to e to the x power. Now again, there is a very common mistake that I see way too much with this. And if you're making this mistake, that's really bad. That just kind of shows me that you're pretty much checked out if you're making this mistake, that you're really not paying a lot of attention. So please be careful here. If you have f of x equals e to the x, right? So let's say this is a problem that you're dealing with and you want to find the derivative, f prime of x. What a lot of people like to do, and in fact, let me just label this as another common mistake off to the side, because I don't want you writing this down and then leaving it and thinking this is correct. What a lot of people do is they try to do the power rule on this. They take the x value, the variable, they bring it down front, they leave e, and they do x minus 1. Okay, that is an absolute no. The power rule works when x is your base and you have a numerical value as your power. All right, so just as a side note here, power rule works, and we'll do it this way. I won't even say x. I'll say when you have a variable raised to a constant. All right, so if it's your variable raised to a constant, e to the x does not fit that mold, right? Because e is a constant, in case you forgot that. E is just a number. So you have a constant raised to a variable. That is a completely different situation. So the derivative of this cannot be resolved by applying the power rule. So the question then is, okay, well then what is the derivative of this function? If f of x equals e to the x, then f prime of x is equal to, ready for it? E to the x. How cool is that? Right? I mean, we kind of started with a nice one, the derivative of a constant is 0. And we're ending with a pretty nice one. The derivative of e to the x, it's just itself, right? It's the one function that's going to do that for us. So the derivative of e to the x is e to the x. Now, there's not a lot we can do with this just yet. All right, this will come in handy. I promise you this will be very useful to us down the road. But there are some other rules for integration. Well, I'm getting way ahead of myself. I'm talking like we're in Calc 2 now. There are some other rules for differentiation that we need to learn first before we can mess around with these exponential functions. So it's all very basic right now. It's just e to the x. So if you encounter e to the x as a portion of your problem set, then the derivative of it would just be e to the x. So as maybe a final example to close things out here, let's suppose that we had a function f of x, and let's just make this something pretty nice. Let's say we have 3x to the negative 2 power plus, I don't know, let's say the square root of x plus e to the x. And let's say we want to take the derivative of this function. So the way we would differentiate it, f prime of x, is, all right, so in the first one, simple power rule, right, negative 2. Bring it down front, you already have a 3 there, so the 3 multiplied with a negative 2 is going to give you a negative 6, x to the, and then replace your power by 1 less, so negative 3, plus, all right, square root of x. Well, what you got to remember there is the square root of x is just x to the 1/2 power. So bring that 1/2 power down front, replace it by 1 less, which is going to give you a minus half, plus the derivative of e to the x, which we just learned is e to the x. So that'd be fine. You could write your answer that way. I also want to just show you that this answer may be expressed in a different way. It's possible that that first term may be written this way. It's possible that the second term may be written this way. The last term isn't going to have any chance to be written differently. Especially this middle one, right? This happens a lot where if you have x to the minus half power, remember x to the minus half is the same as, I kind of skipped a step in there, right? If I was kind of trying to show this all the way through, I might have written it as 1 over 2 times x to the positive half power. So I can get rid of the negative by moving the whole thing to the denominator, but then x to the half power, remember that's just the square root of x. So this type of thing happens a lot. So if you're working through some of the problems and you're, looking in the back of the book or checking somewhere for some answers, and you're getting answers that look like this, right? That's what they're showing you. But the work you're doing is giving you this. Just be prepared to look at potential ways to rewrite your solution. Your answer is still correct. It's just written differently. Okay, I'm going to leave you there with it. That's going to do it for the first section of the new chapter. I hope this makes sense. If you got any questions, you guys know how to track me down. I'll see you next time.